Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the first part of Chapter 8. Now, in this chapter, we will basically give further discussions on constraint optimization problems, which may further used in some modern optimization problems. The outline of this chapter is like this. We will also take a look at the KKT conditions, which is from another point of view, and then we demonstrate the KKT conditions by an example. After that, we will introduce the do problem, how we derive it from a higher point of view, and finally is some concluding remark. Now, let's take a look at the first part, the KKT conditions. Let's begin with an example and consider the following matrix examples. So this example is called the nearest correlation matrix problem. So in finance, people always trying to use their money to buy some assets or stocks or shares. The aim of their buying assets is that to try to maximize their return and meanwhile to avoid the risk. So among these problems, there is a very important fact or a very important part is the correlation matrix, which actually defines or represents different relations between different stocks or shares. So the nearest correlation matrix is actually trying to find a correlation matrix X, which is the closest to a given approximate correlation matrix C. Okay? So the observed matrix C is representing a noised correlation matrix, which may not a true correlation matrix. So we are trying to correct it a little bit to make it a true correlation matrix. So what is correlation matrix? The characterization for correlation matrix is in the following. So we got the diagonal of this matrix to be 1. Meanwhile, this matrix has to be positive semi-definite. So this comes the correlation matrix. And the nearness we measured by the Frobenius norm here, okay? So for this problem, we are trying to find or solve the X here, okay? And there are some typical solvers to solve this problem. The nearest correlation matrix is actually a special case of quadratic semi-definite programming. Therefore, it can be solved by the typical QSDP solver, which was developed by Professor De Fengsun and his group. On the other hand, there are some typical solvers for NCM problem, which is nearest correlation matrix. The typical solver is the semi-smooth Newton's method, which we have introduced before, okay? And this problem is actually can be successfully solved by the semi-smooth Newton's method, and the speed is very fast. Now, a question is, if we want to solve this problem, how can we write down the KKT condition? If we use the way that we introduced in Chapter 7, then we may meet some difficulties. So the aim of this chapter is that we introduce a more general form to derive KKT conditions and do problems. Now, to derive the KKT conditions, let's consider a more abstract form for optimization problem. We consider the minimizing of fx, where this x is in some space. We call it capital X. Meanwhile, X got some constraints, which is characterized by Gx in capital K, okay? So here we assume that the function f is a continuously differentiable function from space capital X to real space. And for the constant capital G, it maps the function or maps the variable from dimension X to another dimension capital Y, okay? It is also assumed to be continuously differentiable. And for the set capital K, it is a set in space Y, and we assume that it is a convex cone, okay? So from this point of view, this problem is actually a conic programming problem. And also, based on the abstract form, we can write down similarly the Lagrange function here. Notice that the first term is the same as before. However, for the second term, we take inner product of mu with gx, okay? So notice that gx is in space capital X. So this parameter mu is actually in the dual space, all right? We will talk about this mu later. Now, let's recall some special cones we introduced before. The one cone is the normal cone, okay? So a normal cone to a set C is defined as the set of all normal vectors D which satisfy the following conditions here. And for the dual cone, as we may recall that it has some close relationship with the polar cone. So for dual cone, we are actually looking for a vector y who forms the angle with all the points in C smaller than or equal to half pi, okay? For the vectors y, if it satisfies the condition here, for all the x in C, then this will be the dual cone, okay? So with the tangent cone and dual cone, then we are ready to present the KKT conditions. Now, let's consider the constraint optimization problem in an abstract form. And if x bar mu bar in space X and Y satisfies the following KKT condition in the feasible point x bar, then we call that mu bar is the Lagrange multiplier. And also here, notice that the nkgx bar is the normal cone of set K at point gx bar. So you can see that the KKT condition takes a form like this, okay? So the first one is the same as before, which is that we take the gradient of Lagrange function with respect to x to be 0, right? However, the second one is different from what we have introduced in chapter 7. It is actually a compact form. It means that 0 is in the right-hand side, okay? So the right-hand side of this part is actually a set, okay? So this set is actually starting from the mu bar and then plus another normal cone. And as we mentioned before, this normal cone is the normal cone of capital K, this set, at point gx bar, all right? So you may wonder, what is the relationship between the KKT here with the KKT that we talk about in chapter 7? Actually, the answer is they are the same KKT conditions, okay? So how could this is possible? So we demonstrate the equality in this page, okay? So why they are equivalent to each other? Let's start from the KKT condition here that we just introduced And the final aim is that we try to get the KKT conditions in chapter 7. Now, we start one line by another line to show the proof, okay? So we start from the second condition here, okay? So the aim is that we try to reformulate this condition as the KKT conditions in chapter 7. Now, if we take a look at this condition, so this is actually equivalent to the case that we move this mu bar to the left-hand side, okay? Then we got minus mu bar is in the normal cone, okay? So the normal cone, this relationship actually implies several conditions. The first one is that Gx bar must be a feasible point of K, okay? Another implication is that by the definition of normal cone, this minus mu bar must satisfy the normal vector condition. In other words, this normal vector multiplied by this term should be non-positive, okay? So this term here is actually we take any elements D from K, all the conditions here will be held, all right? Now, if we write this in more details, then we can actually get two conditions here. So the first one here is the same as before, and the second condition, we can take two special vectors of D. If we take D to be Gx bar, then it means that 0 in K, so we get this condition here. And also, if we write D is 2 Gx bar, then we can get that this will be greater than 0, okay? Then actually, finally, we can get that this condition mu bar multiplied by Gx bar, the inner product of the two terms is 0 actually. So substituting this condition into the condition above, then we can get the third one. The inner product of mu bar with D is greater than or equal to 0. In other words, we have three extra conditions now. So by the definition of D, then we can see that actually mu bar lies in the dual cone of cone K, okay? This is by the definition of dual cone. In other words, now the second condition in KKT, we actually replaced it by the three conditions here in the bottom. Okay, now let's make a big summary about the KKT condition. So previously, the KKT condition, now we can replace them into the four parts, okay? So the first part is the Lagrange gradient to be 0. The second one is x bar is actually a feasible point. The third one is the inner product between the multiplier and Gx bar to be 0. And the final part is that the multiplier must lie in the dual cone of K. If we rewrite the last three parts in another form, then we can write it in the following, that mu bar is orthogonal to Gx bar, and mu bar lies in the dual cone of K, and meanwhile Gx bar lies in the cone. Okay, so this is a more compact form. Now, let's make a brief summary about the first part of chapter 8. In this part, we basically introduce the abstract form of the KKT condition, which can be used to analyze the complicated optimization problems. In the next part, we will discuss more practical examples to show how this abstract form of KKT conditions related to the KKT conditions in chapter 7. Okay, we stop here and see you next time. you.